Okay, good morning, everybody. Uh, I hope people can hear me. Please make some kind of a gesture so I can see that you can hear me. Okay, good. So I have this new microphone, which I'm not used to. Okay, so let me remind you what we did last time. We had a topology. Where did this go? We had a topology on the space of closed subsets of Rn. So this is this notation is the space of closed subsets of Rn, and on this space we have a metric defined by this formula. Is there a question? Okay, I hear something. Okay, so we have this formula, which is the so-called Chaboty-Fell metric. Let me remind you what this metric is measuring. 2 points or two sets, x and y, are epsilon close. If you are looking at a big ball, the smaller epsilon is, the bigger the ball. And the points of the first set intersect the big ball are very close to points from the second set. And close means up to, again, up to this small parameter epsilon. And so you should sort of imagine that if two sets are, to check that two sets are very close to each other, you need both a telescope and a microscope. With the telescope, you look far away in this big ball. And for each ball that the telescope sees, then you pull out your microscope and you look for another point. You look for a point nearby. So the two sets are close if they're close, if they're similar to each other, both on a large scale and on a small scale. And of course, the condition is symmetric in x and y. This is the requirement for x, and there's a symmetric requirement for y. So this metric is called a Chaboty-Fell metric. On the in the exercise sheet, you actually verified that it's a metric, and then we had some necessary and sufficient conditions for convergence with respect to this metric for lattices. So sequence, I'm just reminding you of things from the last lecture. So Lj is a sequence converging to L. I'll be using this index J because N is reserved for the dimension. So lattices Lj converge to a lattice L with respect to this metric if and only if every element of the limit lattice is a limit of sequences Lj coming from the lattice Lj. And conversely, whenever you have a converging sequence in these lattices, even after passing to a subsequence, the limit has to be in the limit lattice. That's B. C is convergence of the bases. And so whatever you have a basis of the limit lattice L, you can find corresponding sequence of bases of the jth n-tuple is a basis for the jth lattice, and each individual element of the basis converges to what it should. So that's the convergence of bases characterization of convergence here. And you can rewrite this in terms of matrices. Um, if you write Lj as the image of Zn under Gj and L is the inverse of Zn under G, then Gj should converge to G, perhaps after right composing with an element of the stabilizer of Zn, which is GLNZ. And on top of that, we proved that these two functions, the covolume function and the shortest non-zero lattice length, shortest non-zero vector length in the lattice, these two functions are continuous with respect to this metric. Okay, so that was the reminder from last time. Another reminder which I want to do is just remind you of the notation or the set of all lattices and the set of all lattices of covolume 1. The set of all lattices was in bijection with this quotient of groups, GLNR over GLNZ. The space of all lattices of covolume 1 was in bijection with SLNR over SLNZ. And in both cases, the bijection has the following shape. You take a coset G gamma, where gamma is either SLNZ or GLNZ, and you map it to the image of Zn under G. And let me introduce a notation now. I want to call this space of lattices of covolume 1, I want to denote it by xn with this fancy curly x. And I want to denote, I'm sorry, I want to denote lattices of covolume 1 by xn, and lattices of arbitrary covolume by xn bar. So that's notation that's I'm going to be using from now on for the rest of the course. So that was a reminder of what we did last time. And with this topology, I'd like to talk about um, sequences of lattices that diverge. So we say that Lj diverges in this space of lattices if the sequence Lj has no convergent subsequence with respect to this metric or topology that we introduced a few moments ago. So as you know, a set in a metric space is compact if and only if every sequence has a convergent subsequence. So this is a definition that we need in order to detect compactness. And so example of sequences which go to infinity if lambda 1 of Lj goes to 0 or covolume Lj goes to infinity or covolume Lj goes to 0, then Lj goes to infinity. And why is that? Well, if that's exactly um, the previous proposition, these functions are continuous functions. If we had a convergent subsequence, for example, if we had a sequence where Lj's converge to a limiting lattice L, then the lambda 1 of Lj would have to converge to lambda 1 of L, which is a non-zero positive number, a non-zero number. So this would fail, and similarly in the other two cases. Okay, so these are examples of divergent sequences in the space of lattices, and then the proposition says that this is the only reason for a lattice to diverge. And so Lj goes to infinity in this space of lattices of arbitrary covolume if and only if one of these things happen. Note that we can't have, I'm sorry, I should have also said lambda 1 goes to lambda 1 of Lj goes to infinity. One of these four things happens. But the last thing I wrote down, lambda 1 of Lj goes to infinity, only happens when the covolume goes to infinity, because we had a link, namely Minkowski's theorem said that if the covolume is bounded above, then lambda 1 is also bounded above. Whenever you have a whenever you have an upper bound on the covolume, that gives you a bound on the shortest vector. So this is included. This case is included actually in this case. Okay, so we already saw one direction. We already saw that if any one of these goes happens, so we saw this direction. If any one of these four things happens, then the lattice diverges. And let's talk about the converse. The converse uses an exercise that was on your exercise sheet. So let me first, so suppose it's a proof by contradiction. So suppose lambda 1 of Lj does not go to 0, and covolume of Lj does not go to infinity or to 0. So passing to a subsequence, I can assume that lambda 1 of Lj is bounded below, and the covolume of Lj is bounded above and below. And we want to show that Lj goes to L, possibly passing to a further subsequence. And this will give us our contradiction. So I'll remind you of a notation that we had. Kappa I of L is length of the ith vector in the Korkin-Zolotarev reduction procedure. So what is this? So there was a way that I described to extract a certain basis of a certain reduced basis, reduced here meaning where the vectors are not too long, a certain reduced basis of a lattice, and it went as follows. I'll just remind you without writing anything down. The first vector in the basis is the shortest non-zero vector, and then suppose you've chosen vector number 1 up to vector j, then you project the lattice onto the orthocomplement of the space spanned by the vectors that you've already chosen. You choose the shortest vector in this projection, and then you look among its preimages in your lattice under the projection, and you choose the shortest one of those, and you continue. So this produces something, and this produces a sequence of vectors, and we showed that this sequence of vectors is actually a basis for the lattice. And then you had an exercise. This is, or you still have the exercise, so I shouldn't say had an exercise. There's an exercise on the exercise sheet. It's number 7, and the exercise is to prove that kappa I is comparable to lambda I, where this notation means A comparable to B means A, B are functions on the space of lattices, and there is a constant C such that for all L, we have this.
Maha, can I ask a question?
Sure.
So since lambda 1 is bounded from below and the covolume is bounded from above, can't you use like some sort of compactness argument to say that the actual fundamental domains converge?
That's another way of doing it, yes. And that's what basically the proof will show. The problem of, let me finish the proof that I'm giving. It's essentially the same idea, and I'll explain why I prefer to work with this Korkin-Zolotarev coefficients. But yes, that's the idea. So, the exercise was to show that the kappa i's behave like the lambda i's. In other words, these constants that appear in this notation are allowed to depend on the dimension, but so maybe I should stress that. C may depend on n. In fact, it does depend on n, and how it depends on n can be very interesting and not very well understood. But for the purposes of this proof, it doesn't matter. And so that's something that I asked you to show in an exercise. And then we have Minkowski's second theorem, by Minkowski's second theorem. The kappa i's satisfy the following bounds. So there is a constant C1. Well, maybe I'll just write it in this form just to make it more consistent. So Minkowski's second theorem says that this identity holds for the lambda i's. But we already know that the lambda i's are comparable to the kappa i's. And also Minkowski's second theorem says that this holds and the constant C is specified. But again, we don't care about the constant in this proof. So this is a corollary of Minkowski's second theorem. So let's check that this implies that actually the kappa i's themselves are bounded from above and below. So the co-volume is bounded from above and below. The kappa i's are not, strictly speaking, in increasing order, but the lambda i's are in increasing order. And we know that lambda 1 is bounded from below. So this is, let's put in the j's now. We're on this subsequence. So this is bounded below independently of j by some constant that does not depend on j. That's part of our hypothesis. And this is also bounded above and below by some constant independent of j. Okay. And so let's prove that lambda n is bounded above. So lambda n of Lj is less than a constant times the co-volume of Lj divided by lambda 1. Okay, I moved in Minkowski's second theorem, imagine that this had lambda i's instead of kappa i's. I moved all the lambda i's except the last one to the other side, and this is less than, since the lambda i's are ordered, this is less than this. And this is bounded above by some number independent of j. And therefore, all the numbers kappa I, so this implies for all I, the lambda i's are bounded above. Again, all the time by some number independent of j. The same is therefore true for the kappa i's. And so passing to convergent subsequences, we know that the vectors whose length, so if Vij is the vector whose length is equal to kappa I of Lj, and these vectors are giving us a basis of Lj, then the vectors Vij passing to a subsequence converge along J. So then passing to a subsequence, these vectors converge. And this implies, since this is a basis, this implies that Lj is a convergent subsequence by part C of the proposition. So I had several necessary and sufficient conditions for convergence. One of them was involving bases, and I've shown that the bases converge, and so I get convergence. Okay, now the question that Shai asked was, why should I work with the kappas? Why don't I work with the lambdas? Or why don't I work with something like a fundamental domain geometrically? You can work with fundamental domains geometrically, then you have to make sure that in appropriate topology, the limit of a fundamental domain is actually a limit of the limiting lattice, which I didn't do. You can do it, but I didn't do it. It's more convenient to work with the kappa i's than to work with the lambda i's, because as we said several times, the lengths, there are vectors realizing the lambda i's, but they don't form a basis. And so the kappa i's are more convenient because they're measuring lengths of vectors which do form a basis. Okay, so that's the proof of this proposition. And the corollary is something quite important called Mahler's compactness criterion. And it's also known as Mahler's selection principle in the classical literature. So there's some interesting thing with terminology when it comes to lattices. Lattices, I mean, geometry of numbers is an old topic. So some of the words that people use, some of the terminology is very old fashioned. So in the early 20th century, people were not so comfortable or not so used to talking about topology all the time. It's very common for us to talk about a compactness criterion. It wasn't so common in the beginning of the 20th century. Selection just means you want to be sure that you can select a convergent subsequence, which is basically what compactness is all about, but this is kind of the classical name. Okay, so let's let pi be the projection from SLNR to what we're denoting by fancy X of n, the space of lattices of covolume 1, SLNR over SLNZ. So pi is just the map that sends a matrix in SLNR to the coset of SLNR over SLNZ, or in other words, it's the map that we had before. It maps a matrix G to the lattice G applied to Zn. And we want to know, given a set in SLNR, we want to know if it projects to a compact subset of the space of lattices. And so then for S, a subset of SLNR, pi of S closure is compact if and only if there exists an epsilon such that for all x in S, lambda 1 of pi of x is bigger than epsilon. So why I don't even need to prove this. Basically what this is saying is that on the image of S, lambda 1 is bounded below. And the previous proposition, where did it go? Said that every sequence has a convergent subsequence. A sequence has a convergent subsequence if and only if all of these happens, lambda 1 is bounded below. So the only obstruction for the only reason to go to infinity is for lambda 1 to go to 0. Or another way to say it, if you rule this out, and you rule this out, and you rule this out, then you cannot have sequences converging to subsequences converging to infinity. Then every sequence has a convergent subsequence. Now, why didn't I stick in requirements about the covolume? It's because I'm here I'm in the space of lattices of covolume 1, so the covolumes are normalized. So the previous proposition says that the only reason not to have a convergent subsequence is for lambda 1 to go to 0. And so if I don't allow lambda 1 to go to 0, then I don't have convergent subsequences. Okay, and because the previous proposition was if and only if, this is also if and only if. Questions about this?
Does Muller's theorem have a generalization to lattices which are not in Rn, like in other?
Yeah, so I'm going to show something like that soon. It's quite easy actually to. Do you mean smaller rank discrete subgroups of Rn, or do you mean lattices in some space isomorphic to Rn which is not Rn?
maybe Lie groups or something like that, or is it?
For general groups. Yes, there's a version of this for topological groups, and this is due to Chaboty. And so the name of the topology that we're using is the Chaboty-Feld topology. Where did this go? The metric, yeah, this name here, Chaboty, is a French mathematician. So in the 40s, he wrote exactly a paper explaining for sequences of discrete groups in a topological group, when do they have convergent subsequences? And he proved basically a statement which is very, very similar, a generalization of Mahler's compactness criterion in a non-abelian setting. It's not exactly the same. Let me just think for a moment if it's precisely the same statement. So there's an issue about measuring lengths in a non-abelian setting. You have to decide whether you're choosing which metric you're choosing. In particular, sometimes there's a right invariant metric versus a left invariant metric. So modulo some technicalities like that, there's a precise generalization to a general Lie group setting, a general topological group setting, in fact.
Thank you.
Okay. Yeah, good question. And also, I should say, okay, let me leave it at that. There's some exercises in the exercise sheet about taking limits in this topology, and there's kind of this basic principle that often limits of groups are groups. That has nothing to do with lattices. It's just a general fact. Let me state the compactness criterion in another form which is often used. So equivalently, let's define a subset of the space of lattices of covolume 1 where the shortest non-zero vector is bounded below by epsilon. Then the compactness criterion is saying two things. It's saying that each k epsilon is compact, and it's also saying that whenever you have a compact subset of the space of lattices of covolume 1, it's contained in one of these k epsilons. So in topological, these two things taken together have a name in topology, i.e. the sequence of sets k epsilon are an so-called exhaustion of this space. So an exhaustion of a space is a sequence of compact subsets which fill up the space and have the last property, namely that every compact set is contained in one of them for a suitable value of the parameter. And I think they should be nested in general, and they're nested. Obviously, they're nested here. So this is the Mahler compactness criterion, or the Mahler selection theorem. Let's use it to talk about certain, we have a little bit of an unfinished business with things we were discussing previously. So applications, let's just show one application, but it's sort of typical. So here's a corollary. We had a notation, alpha r of L was the infimum of the covolume of L0, where L0 is a primitive subgroup of L of rank R. And I said without proving that this infimum that appears in this definition is actually a minimum. So in other words, that there is an L0 which realizes this infimum. So the corollary is that there exists a minimizer here. There exists L0 of L primitive of rank R such that the co-volume of L0 is alpha R of L. Let's prove that. So this is kind of a typical application of the Mahler compactness criterion. So by definition of this quantity, since it's an infimum, you can find a sequence of these L0s which come closer and closer to realizing this number. So let Lj in L be primitive subgroups of rank R such that the co-volume of Lj converges to alpha R of L. Using exercise 7 again, in other words, I want to choose a nice basis for Lj. So there exists a basis uj1 up to ujr of Lj such that the norm uji, which is what we noted by kappa I of Lj, is of comparable size to lambda I of Lj, the ith Minkowski successive minimum of the lattice Lj. And again, we have the inequalities that we had before. So as in the previous proof, we can bound, there's a constant here. There should be a constant here for some C. And this uses Minkowski's second theorem. Okay, we get these bounds. And so the lambda i's are, and this, all of this is taking place. All of these lattices live inside L. These are not lattices, in fact. These are just, these are rank R subgroups. And these rank R subgroups live inside a fixed lattice L. So all of these numbers are bounded below by a fixed positive number, which is the shortest non-zero vector of L. And so these lengths, the lengths of these vectors are bounded below by this number, and they're bounded above by this number. And this number is bounded independently of J because this is a constant, and this tends to alpha R. So that's also bounded. And again, this is bounded below by this inequality. So this entire quantity is bounded above. So now we pass to subsequences. So these are vectors in Rn, which are bounded above and below, and we can pass to subsequences. We get this. And the UIs are contained in L because the UIJs are contained in L, and L is closed. And so what have we achieved? We can define L infinity to be the span over Z of U1 up to UR, and then the co-volume of L infinity is the wedge, is the norm of the exterior power of U1 up to UR, which is the limit as j goes to infinity of the norm of the exterior powers. And this is exactly the covolumes. And so we've constructed a particular element, which is a rank R subgroup of L infinity, which realizes this quantity. And that's so the minimum. So the minimum is attained. Okay. Here's kind of another proof of the same fact that you're also likely to see. So alternative proof. Let's write L as G times Z of N. Z of N is the integer lattice, and let's write each Li as before is the span of these. So I start the proof in the same way. I consider a sequence which converges to a sequence of LIs whose covolume converges to this alpha R, and let's take a basis of these LIs, denote them in the same way. And this is a vector, so Uji is a vector in Li, so it's a vector in L, so I can write it as G times V Ji like this, where Vji is in Zn. So let's look at this exterior power of, first let's look at the exterior. We care about the limit of the exterior product. We have this formula for the covolume. So we care about the limit of this exterior product. Well, before computing the exterior product of these vectors, let's compute the exterior powers of these vectors. And so we have the Vj1 wedge, etc. Vjr, and this is an element of the space we called lambda, the rth exterior power of Rn, or we also called it, we had this notation. These were two notations. This is the rth, the space of R tensors space of R vectors in the Grassmann algebra. And it has integer coefficients. With respect to the basis we used a standard basis. E sigma, where sigma is an R tuple. Okay, these formal symbols, E sigma, were generators, were a basis of this space. And if you express each one of these vectors individually in the standard basis, it has integer coefficients. And we had a formula for the coefficients of a linear combination involving minors of some determinants of some minors. And so with respect to the standard basis, this exterior power has integer coefficients. Okay. Now since this thing converges, so does this thing. Right? What's the mapping that sends the mapping G sends vectors to vectors, and so it acts on this exterior algebra, and it's acting on the exterior algebra in a continuous way. So if this R tensor here converges, then so does its image under a continuous map, the map G by G inverse. So this also converges, but this is these are vectors with integer coefficients, and so they live in a discrete set in this space. And so since the z-span of these sets E sigma is discrete, this length is eventually constant because it converges in a discrete set. And therefore, this is also eventually constant. Okay, so that's another way of proving that this minimum in the infimum in the definition of alpha R is attained. Okay, so oops. Okay, so that's one application. Another application which will be more interesting for us and is going to occupy our attention for at least 2 weeks is to the maximal packing density. So let me remind you what the maximal packing density is. So reminder. So if you have a lattice, you define its packing density as so in words, it's the maximal, it's the proportional space that you can fill up with balls which are disjoint and centered at the lattice points. And so what this comes out to be is the volume of the ball whose radius is lambda 1 of L over 2 divided by the co-volume of L. So let's go to a picture that I showed you a few weeks ago. So this is these points here are points of the lattice. In fact, this is the hexagonal lattice. This hexagon here, the interior of this hexagon, this is a fundamental domain. It's the Voronoi cell of this lattice. And so its area is the co-volume of the lattice. And these balls here are a maximal collection, maximal in terms of radius, of balls of equal size centered at the lattice points. And the quantity that we're measuring is down here. It's the volume of one of these balls divided by the volume of the fundamental domain. And we can also see if this length here is lambda 1, it's the length of the shortest vector in the lattice, then the radius of this ball is exactly half of lambda 1. So this is lambda 1 divided by 2. Okay? So the volume of the ball is lambda 1 over 2 to the power n times Vn. Vn is the volume in Rn of the ball of radius 1. This is a kind of a well-known constant. We don't really care about this constant, just some normalization constant for us, but its asymptotics is kind of very well studied. And so this is the volume of the ball whose radius is this number. And the volume of a fundamental region is the covolume. Okay, so this is the packing density of the lattice. So let me write down that formula that I just explained. So we get this quantity, which is the proportion of space filled by non-overlapping balls centered at points of L, maximal proportional. And then the quantity that people are very interested in is the number delta n, which is the sup of delta of L for all L. It's the maximum packing density that you can achieve by trying to cover space with a system of balls centered at lattice points. And the corollary of the modular compactness criterion is that this sup is actually a max. Which means that in each dimension n, there is a lattice L so that its packing density is the maximal possible packing density. I'm going to prove, this is an easy proof. I'm going to prove it, and I'm also going to introduce another variant. So what we're looking for, L such that lambda 1 to the L divided by, let's call it L0, co-volume of L0 to the power 1 over n. This is greater than or equal to lambda 1 of L, co-volume of L to the 1 over n for all L. Right? If I want to maximize, that's just this formula here. Where did it go? Sorry. If I want these two elements, I'm trying to maximize this quantity over the space of lattices. This is a constant depending on our dimension. This is a constant depending on our dimension. So I need to maximize this quantity. And maximizing this quantity is the same as maximizing the same quantity taken to a power 1 over n. So taking power 1 over n, this becomes lambda 1, and this becomes co-volume to the power 1 over n. So that's why this is what I want to maximize. Let me write down another quantity that won't be important in this proof, but will be important later. So equivalently.
Sorry, can I
Sure.
just, can't you assume that the co-volume is 1?
I can assume that the co-volume is 1. Because when you, one way to see that is that when you dilate when you dilate a lattice by a constant, the length of its shortest vector changes by that precise constant, and the co-volume changes by that constant to the power n, and so this quantity remains unchanged. But I'd like to have formulas where the volume is not normalized because they're going to play a role later. It's not really important for this proof, but it's sort of, I'm setting things up so that I can use it later. Okay, so and another thing I'm setting up is another notation, which is the so-called Hermite constant. So I'll just define it now. So mu of L0, which is defined to be lambda 1 of L0 squared divided by co-volume of L0 to the 2 over n is maximal. So this is called the Hermite constant. And it's basically another measurement of the same thing. This quantity is just the square of this quantity. But for various reasons, I'm going to remark a little bit about that later. Historically, people considered this quantity where you square things. And so maximizing any of these quantities is the same. So let's take now a sequence of LJs. And as Manuel anticipated, we can take them to be in Xn. So they're coming closer and closer to achieving this soup. So I want to show that they converge, and this is so the lambda i's are obviously bounded below, I'm sorry, because they're converging to this number, which is a positive number. And so by the modular compactness criterion, along a subsequence, we have convergence. And so by continuity of this quantity, we get what we want. This is because lambda 1 is continuous in this topology. So the maximum for the lambda 1 quantity is attained, which is the same as saying that the maximum for the delta quantity is attained, which is the same as saying that the maximum for this Hermite constant quantity is attained. And we're going to discuss the kind of very famous problem of what is that maximum and what is this lattice that maximizes this packing density? It's sort of called what is this optimal? So we now know that there's an optimal way in each dimension to pack balls using lattices. And the question that we want to discuss is what is that optimum way? And that's our next topic. So let's take a 10-minute break and discuss that after the break.
Barak? Barak,
Again,
is there some sort of uniqueness to like the optimal lattice, which
yeah, we're going to be discussing exactly that question. So basically, as you're going to see, the answer is there are only finitely many possibilities for it. That's kind of a general fact, but how many there are and whether it's actually unique is not known in general.
Mhm. Do we understand like the asymptotics of
No,
the?
no, that's the kind of a holy grail of the whole topic. Not known. So I mentioned this briefly in a previous lecture, and we're going to be discussing that question quite in detail.
Thank you.
Okay, let's go on. Um, so I'd like to say a few general words about this lattice packing problem and history and what's known, and then we'll start saying a few things. I hear some noise in the background, so either people want to ask questions or you're not muted properly. Questions? All right. So, some history of this lattice packing problem. So the question can be asked in any dimension, and there are partial results in some dimensions. First of all, it's on Hilbert's list, so it's Hilbert's 18th problem. Has 3 parts, and the third part of the problem is, what is the densest sphere packing in R3? What about other shapes? And so what is this problem? So you can ask about a lattice packing problem, which is what's the most efficient way to pack Euclidean balls in R3. You can add the extra restriction that the balls have centers. The balls always should have equal radius in this problem. For whatever linguistic or historical reason, in this topic, spheres are balls. In this sphere packing, this ball packing problem is often referred to as a sphere packing problem for some reason. You can relax the requirement that your centers form a lattice. So that's a more general type of packing, and it's harder to analyze. Although this working with lattice packings is also quite difficult to analyze, as we'll see. You can fix your favorite shape, which might be a simplex, or it might be an LP ball. In some cases, it's trivial, like for cubes, it's clear that you can pack cubes tightly in space with density 1, but for general shapes, it's absolutely unclear how to pack them densely. And in each, one of these specific problems has attracted a lot of attention. So Hilbert was asking about packing balls, not necessarily along lattices in R3, and he was somehow implicitly assuming that he knew what was going on in dimension 2. The way the history of the problem works is that there's sort of a bunch of results, a bunch of claims, and later generations find mistakes in the proof, and the proofs are very, very complicated. So the packing problem in dimension 3 was solved by, so this problem was solved by Hales very recently, so 1998. I'm going to say a few words about that. So let me move up to show you some pictures. Where is this? Yeah, so this is the problem first came up in connection with a British mathematician and astronomer by the name of Harriot, and he sent a letter to Kepler in the very early 17th century. I think it was around 1605. You can see the letters and the dates on the Wikipedia page. And Kepler published a paper called the six-cornered snowflake in 1611. And in the paper, there was this picture of a packing of balls in three-dimensional space. This is the packing that you see when you go to the market to buy oranges, or when you go to a bowling alley to look at bowling balls, and so on and so forth. So many people sort of intuitively believe that this is the optimal packing in space, and the question was, is this really the optimal packing in space of balls of equal size? And so the question goes is far, far older than Hilbert's list of problems, which is from the from 1900. And this problem was open for a very long time with lots of incorrect proofs proposed, and it was finally settled recently by Hales, and I'm going to say a little bit about that in a moment. Here is what's known about the um, same problem for lattice packings. So I've made a table here. This is the, oops, this is the dimension, this is the lattices, this is the year it was proved to be optimal and who proved it. And this is the question about whether the lattice packing is also the optimal packing of space in that dimension. So, okay, so the lattice packing problem is proved in a total of 9 dimensions. So I'm not mentioning dimension 1 because it's trivial, all the way up to 8. It's solved, and then there's a magical lattice in dimension 24, which also solves it, and this is called the Leach lattice. Okay, what about these names? Lattices have names, and there are these letters here. There are some letters that if you've taken a group course on Lie groups, in the classification of Lie algebras, there's a certain type of very special graphs called um, um, root systems. And there's a classification of these root systems, and these are examples of these root systems. These root systems show up in many, many other problems in combinatorics, including this. So they give rise to lattices. They also give rise to actions of tilings of certain spaces, and they are part of the classification of Lie groups and Lie algebras. So all the lattices in the list, except for the one in dimension 24, are associated with Lie groups via root systems. You see the list of people involved in this project. First of all, you see that there's a big gap in the years between successive developments. Second, you see that it's kind of an illustrious list. We're going to discuss this work here. So we're going to discuss the strategy that Korkin and Zolotarov, 2 Russian mathematicians, took in order to understand the how to solve this lattice packing problem, and they managed to do it in dimension 4 and 5. Voronoi came along about 30 years later and set things up for the solution in dimensions 6, 7, or 8, but he died young. He died shortly after his paper. I think this, I don't remember the date of death, but I think his work was published after he died, which is around this date. And Blichfeld completed this. So he got the things up to dimension 8. The lattice E8 is a lattice that I already defined for you. I gave an example of a lattice with lots and lots of vectors, shortest length vectors, and this is an example. Then there's the question of whether the lattice, the optimal, so in other dimensions, 9 up to 23, 25 and higher, nobody knows the optimal lattice packing, and that's a wide open question. And then once you have the optimal lattice packing, you can ask about the optimal packing period. Now, in the problem of non-lattice packings, it doesn't make sense to talk about the uniqueness of an optimal lattice packing. You can always take a packing of space and remove a few balls from it. It won't change. So first of all, the definition of the packing density for an arbitrary packing is not, there is no fundamental domain, so you can't use the definition that we gave. So instead, what you say is that the density of the lattice is just the proportion of occupied space occupied by the balls divided by the space of a subspace, a big ball or a big cube. As this cube becomes larger and larger in space, you take a limit. So obviously, if you have a packing and you sort of randomly change it locally, it won't affect the eventual density. So one shouldn't expect there to be a unique packing just in terms of definitions. But you can still ask whether the optimal packing is attained by a lattice packing, and this is also an open problem. I think for many years it was believed that optimal packings in n-dimensional space should be lattice packings. And now I think that people no longer believe that's true, but there are no counterexamples. There's not any dimension in which it's known that the optimal lattice packing is not the optimal ball packing. Okay, proof of optimality. I mentioned earlier that Hilbert believed that the hexagonal lattice that we already saw is optimal in dimension 2. There were proofs around of this fact in the 19th century, but there were mistakes, there were gaps discovered in the proofs, and a rigorous proof was first given by Feuchthoff in 43. And the Kepler problem occupied, as you see here, almost 400 years until it was finally resolved by Hales, proving optimality. So that's the lattice packing, which is optimal. There was a huge breakthrough 3 or 4 years ago associated with the name of Marina Wiazowska. Wiazowska proved that this E8 lattice, which was known to be the optimal lattice packing in 34, is also an optimal packing of balls in general. She did this very recently, and this is, this was a very exciting breakthrough. And then with co-authors, she also proved the same result in the 24-dimensional case for this Leech lattice. And one more thing, which is very interesting about this problem, I've put in some pink color in this table. The pink color denotes proofs that involved a heavy computational component, okay? And so what Hales did in 1998, so there had been reductions of this ball packing problem to a finite combinatorial problem. But it was a finite combinatorial problem, it was still a very big combinatorial problem. And Hales programmed a computer to solve this combinatorial problem. And this was a huge computation, so it was quite a non-trivial task. And the computer eventually gave an answer, and the answer indicated that this ball packing, this standard ball packing by lattice ball packing, is indeed optimal, the Kepler conjecture. And he submitted it for publication in the Annals of Mathematics, which is the most prestigious journal in mathematics. And the editors didn't really know what to do because it's a computer-assisted proof. It's the largest. There had been computer-assisted proofs of famous open problems before. It was the largest computer-assisted proof ever to that date. And it's kind of unclear how you check a computer-assisted proof anyway these days. So you can check the reduction of the full problem to a combinatorial problem by hand, and this is what was done. And then you can check and then somehow, how are you going to check the case-by-case analysis, particularly if there are millions and millions of cases done by computer. So the editors of the journal published an open letter saying, we checked what humans could check, and we hope that the computer didn't make a mistake. And this was published. And Hales was not very satisfied with this outcome, but that's where things stood in 1998. Let me move chronologically. I'll come back to this in a moment. Let me move chronologically to 2004. In 2004, Khan and Kumar published a computer-assisted proof of the fact that the Leech lattice is the optimal lattice in dimension 24 for packing. And this was, again, a proof by computer. It was, again, a huge proof. I think also it's kind of hard to say what it means for a proof by computer to be the largest proof by computer ever. But in any case, it was one of the largest computer-assisted proofs ever undertaken in 2004. And similar story. So it also published in the Annals of Mathematics, also impossible to check on some level. This work of Wiazowska and co-authors, including the two, you see that these are the same co-authors. It doesn't make this work redundant. It builds on this work. So you need to know that the Leech lattice is the optimal lattice packing in order to apply the technique of Wiazowska, okay? So this result, even though it's not computer assisted, relies on the truth of this earlier result. Okay, what happened in 2015? Well, Hale was not satisfied with the situation of having published a computer-assisted proof. And what he set out to do was to prove by computer that the computer-assisted proof was correct. So there's a notion of computer verifiable proofs. If you make your code um, conform to a special standard of rigor, a computer can check that the code the code actually proves what it says it should prove, and that the code didn't make the run was done accurately. I mean, there was no you don't want a sudden surge because maybe it's warm, maybe it's a warm day and the humans are warm, so they turn on the air conditioning, and then there's a surge of electric power, and the computer makes a malfunction, and it says that the some lattice is optimal when it isn't. So you want to prevent that. So you run a separate computer program to check the computations of the first. So it's a whole field that I'm not too familiar with, but there's this notion of computer verifiable proofs. And so the Hale's 2015 proof is another huge computer-assisted project, and it's also the biggest ever computer verifiable computer-assisted proof. And so that's the latest. So here we have a proof of the Kepler conjecture, and here we have a proof by computer in 1998, and here we have a proof by computer that this proof is correct. And both are huge computations, if you care about that. Okay, questions about the history. One more question that I was asked during the break is about the asymptotics. So what is the optimal packing density for large dimension n? How does it grow as a function of n? I mentioned that briefly in a previous lecture. The current world record is held by Akshay Venkatesh, who has the optimal to this date lower bound on the packing density in large dimensions. And there's a huge gap between the known lower bounds and the known upper bounds. So that's also very well-known open problem. It sounds like a pure math problem of only abstract interest, but it also has huge technical implications for electrical engineering. And so it's widely open what the behavior of the optimal packing density is, lattice packing density is in large dimension. We're going to spend quite a few weeks discussing getting the lower bounds in that problem. Any questions about the problem, the state of the problem? Okay, so let's start discussing. So what we're going to be discussing, I'm sorry for the flipping. We're going to be discussing the technique that was used in these results. So the proof of optimality in dimensions 4 through 8, done in the 19th century, essentially, or early 20th, follows a certain pattern, and that's what we're going to discuss next. So it's kind of low analysis of the, so we know from the previous result that there is an optimizer, there is a lattice achieving the optimal lattice packing. And we want to figure out something about its geometry in order to find it. And that's the method that was started by Korkin Zolotarev and improved by Voronoi. And then later, Voronoi improved the method, and then it was carried out successfully by Blichfeld. So definition. L is called extreme. Let's call it L0. L0 is called extreme if the function L maps to lambda 1 of L divided by covolume of L to the power 1 over n achieves a local max at L0. Okay, so we're trying to find the lattice which maximizes this quantity among all lattices of dimension n. And so it's a maximum on the space of lattices of this particular function. This is a real number valued function on the space of lattices. And since it's a topological space with a metric, we can also talk about local maxima. And so instead of finding the maximum, we're going to find the local. We're going to be discussing the local maxima. And if you have a local maximum, then you call this extreme. So this strategy followed for finding optimal lattices in dimensions n from 2 to 8 is roughly the following strategy. Step 1, you show that if L0 is extreme, then L0 is perfect, and I'll define what perfect means in a moment. I'll define it later. So this is some restriction on the geometry of this lattice. It's saying that the lattice has lots of short vectors of equal length and saying something geometrical about them. And well, actually, I think the word I'm using, extreme, is incorrect. Let's call this critical. I think that's the terminology that I want to use. And let's say extreme. What we're looking for are the extreme lattices where the global maximum is achieved. And so if you're extreme, then you're critical. So a global maximum is also a local maximum. And here, this perfectness condition is true both for the extreme lattices and for the critical lattices. So, okay. Please stop me if I'm not being clear enough. Second step of the proof, you show that the number of critical lattices, of perfect lattices in any fixed dimension n is finite up to dilations and orthogonal transformations. So let's talk about this for a moment. So if you apply an orthogonal transformation, since we're measuring the shortest length of the shortest vector with respect to the Euclidean metric, if you take a lattice and apply an orthogonal transformation, you're not changing the length of the shortest vector, and you're also not changing the covolume. So this quantity doesn't change when you apply an orthogonal linear transformation. Also, if you dilate the lattice, which means you multiply it by a scalar. If you multiply it by a scalar, lambda 1 gets multiplied by the same scalar. And as we discussed, the covolume to the power 1 over n also gets multiplied by the same scalar. So this quantity also doesn't change when you apply a dilation. So obviously, the critical things are not going to be unique, or the extreme things are not going to be unique. They can only be unique up to dilations and orthogonal transformations. And step 2 says, well, maybe it's not unique, but the number of candidates is finite in every dimension. Again, perfect is, we haven't defined it, but it's implied by being critical. Okay, step 3, you have a finite list of candidates, and you just enumerate all of them. And find the one for which this quantity is maximal. And step 4, show that L is critical if and only if L is perfect and eutactic, which I'll also define later. And the number of eutactic lattices in any dimension is finite, again, up to dilations and orthogonal transformations. Okay, so let me just put names on these steps. So this first step was done by Korkin and Zolotarev. The fact that the number of perfect lattices is finite was done for general dimension by Voronoi. The task now of enumerating the perfect lattices in your favorite dimension and finding the optimal one was done by Korkin and Zolotarev for n equals 4 and 5, and Blichfeld for n equals 6, 7, and 8. And so obviously, logically speaking, you don't need to do step 2 if you're able to do step 3. I mean, if you can just show by brute force that you have all the perfect lattices and it turns out to be a finite list, then in your favorite dimension, then you get step 2 as part of step 3. And that's what happened in this Korkin-Zolotarev proof in the 19th century. And step 4 is very interesting, and it shows that historically it came last. This also is due to Voronoi. And this is also due to Voronoi, both of these facts. And basically what step 4 is showing, it's not strictly speaking needed in this logic, but it's showing that everything that could be done with perfect lattices could also be done with eutactic lattices. So this is another geometrical property. And in fact, there's a necessary and sufficient condition for a lattice being critical, and that's due to Voronoi. Okay, so this theory is we're going to be developing today and next week. And so I want to start off by explaining perfect. And
so
yeah,
I'm still a bit confused about step 4. What you're saying is step 4 gives you a different approach to proving.
4 gives you two things.
A different notion or something.
It gives you a different geometrical notion, which is eutactic. Historically, it came later. Nowadays, with computers, people are starting to think that maybe this notion is actually more interesting than this notion. But historically, this was kind of a side remark. And what Voronoi showed is that you actually gave a necessary and sufficient condition for being critical in terms of both of these notions. But both of the notions in the strategy can play the same role. Okay. So in order to define both perfect and eutactic, I need to talk about the space of symmetric matrices. And I'm going to start off talking a little bit about symmetric matrices, and which seems irrelevant at this point, but you'll see it's very, very relevant. I'll explain that later. So I'm going to, symmetric, oops. I need some facts about symmetric matrices, which you may know from linear algebra. So this is my notation for symmetric matrices in n by n matrices. And this is my notation for the transpose T. So these are matrices which are equal to their transpose. And let me remind you of the connection with the standard inner product. So the transpose has the property that it moves to the other side of the standard inner product. So this means so in general, if you have an inner product of two vectors and you multiply one of the vectors by a matrix, if you want to flip the matrix over to the other side, there should be a transpose here. And it's easy to see that you have this identity if instead of A, you have A transpose. So clearly, if A is equal to A transpose, then this is also true. And it's not hard to check that this is necessary and sufficient for being symmetric. If this holds for all, just use the standard basis vectors and you'll see that this is exactly equivalent to being symmetric. So the space of symmetric matrices, I want to think about it as a vector space. So sim n is a real vector space of dimension n plus n plus 1 over 2, n times n plus 1 over 2, right? You have to fix the values of the matrix at the all the diagonal entries and all the elements above the diagonal, and then the others are determined by the symmetry. So this is the number of possibilities. And facts about symmetric matrices. So any symmetric matrix can be diagonalized over the real numbers. In other words, the eigenvalues are real, and you can do the diagonalization by an orthonormal transformation. In other words, what I mean by that is that it has n linearly independent eigenvectors which are orthogonal to each other. And so there's just a matrix O in O and R. These are the orthonormal. This is the group of orthonormal matrices. A matrix is one way to say orthonormal, and a matrix is orthonormal if its inverse is equal to its transpose. And so to say that you can diagonalize by an orthonormal transformation is to say that there exists a matrix which is orthogonal such that O transpose AO is diagonal. And of course, with real entries on the diagonal, because everything that we're saying is real. Another important thing is that A is called positive definite. If the eigenvalues a symmetric matrix A, of course, is called positive definite if the eigenvalues are positive. And this happens if and only if I can define a quadratic form by this formula. X maps to the inner product of AX with X, and this is non-negative and only 0 when X is 0. So that's another way of detecting a matrix being positive definite. And if A sorry. So this also happens, sorry. This also happens if and only if you can find a matrix B in GL and R such that A is B transpose B. And so the proof, this last fact is something that this last fact that this is equivalent to being positive definite is something that you may or may not know. So let me explain how this proof goes. Proof of last equivalence. There are two directions here. One is easy and the other is slightly harder. So if A is B transpose B for some invertible matrix B, then for any X in Rn, A XX is, or let's write it this way to make it nicer. XAX is X B transpose B X, which is BX BX, which is positive for all X non-zero. So that gives us this characterization of positive definite matrices. And in the second, in the converse direction, suppose we know that a matrix is positive definite. So if A is OD, O transpose OD, where D is D is a diagonal matrix with beta i's on the diagonal, then you define the square root of D to be the diagonal matrix whose diagonal entries are the square root of the elements on diagonal of D. So the reason this is called a square root is that if you take this matrix times itself, you get this matrix. In general, you can't do that, but here I've used the fact that the beta i's are positive real numbers. And now you define B to be, use the same O and B to be O transpose square root of D times O, and then B transpose B is, well, you do the okay, let me just leave it. So you just compute, using this, you just compute that B transpose B is A. So this is, these are facts that are standard about symmetric matrices, which we're going to need. This is studied in the course on linear algebra, but there's always sort of it's sort of the last breath for many first-year students, and many things are skipped. So I just want you to have a kind of a picture in mind, which will be important for the for what happens later. So this is like a cartoon. This is the symmetric matrices. So this is a vector space of some dimension. Inside it, there's a special point, which is the identity. There's another special point, which is 0. There's a subcollection of positive definite symmetric matrices. So I'll just do it in color. So these are like the positive definite matrices. So this is a subcollection of the symmetric matrices, which contains identity in its interior, and the rest of the space of symmetric matrices is made. And this is not important, but this picture is important for us. Okay, and the way we're going to think about this picture is we're going to think about the symmetric matrices in two different ways. It's going to be the space where the positive definite matrices live, and it's also going to be the tangent space to the space of positive definite symmetric matrices. What I mean by that is you can think about tangent directions in the space of symmetric matrices. So you can think of a little neighborhood of 0, and then you can map it just by adding it to the identity, and you get a set of directions in the space of positive definite matrices. And these directions will fill out a little neighborhood of the identity in the space of positive definite matrices. So the symmetric matrices are playing the role of the tangent space to the positive definite matrices in this proof. So I'll just write that. That's just a kind of an intuitive discussion. I'll write that in green. So for us, sim n will play the role of a tangent space at identity of positive definite matrices. Okay. And you might ask yourself, just to complete the picture, we won't need this later, you might ask yourself, well, what does the rest of this vector space look like? And the answer is that there are two kinds of matrices in here. There are the matrices which are not invertible, but all the ones which are invertible correspond to quadratic forms, and quadratic forms have signature. So this space is split up into n+1 little pieces, and you know, just to add another one, maybe there's another piece here, and maybe there's another piece. I don't know. I'm enjoying using my colors, but these correspond to quadratic forms of different signatures, PQ. Okay, so if you're familiar with that picture, that's sort of the picture that you should have in mind. Okay, so why do we care about? Okay, let me use these notions of symmetric matrices, and then I'll explain why they come up in our proof. So you can, on this vector space of symmetric matrices, you can think of each vector as giving rise to a linear functional in the same way. So for x and Rn, define phi x. Phi x takes a symmetric matrix A and computes the quantity AXX that we saw before. So this is a mapping, and note that phi x is linear. So it's an element of the space of linear functionals on symmetric matrices. This is a little bit of a confusing thing in this proof. This expression in terms of x, if x were the input, this would be a quadratic form. In other words, if you multiply x by a real scalar, this thing multiplies by the scalar squared. If you think about this as a formula, it involves squares. But if x is fixed and you're thinking about this as a formula of A, this is a linear transformation. And so it's an element of the dual space of the space of symmetric matrices, and we're going to denote it by phi of x. And now we can finally define perfect. So definition. First, we define a notion of a perfect collection. So let F in Rn be a finite. Well, it doesn't have to be finite. Be some subset of Rn. And so F is called perfect if these mappings, span the dual. Where the x's range over elements of F. Okay? So you have sufficiently many vectors in your collection so that these linear functionals span the dual space of the space of symmetric matrices, and then the vectors given a lattice, the vectors in the lattice which achieve the first, which are the shortest non-zero vectors, so lambda 1 of L equals normal V, these vectors are called the minimizers. For L, and they're denoted by min of L. So some lattices have only two minimizers, so there's the shortest vector and there it's minus, but some may have more, and this collection is called collection of minimizers, and then L is perfect if min L is perfect as a collection of vectors in Rn. So that's the definition of a perfect lattice. Let's do some examples here just to explain this. So examples, let's just work in 2 dimensions so we get the flavor. So let's talk about a lattice. So this is the first example. The lattice is the sum of space, the vectors, the first element of the standard basis plus the integer multiples of 2 times the second lattice, the second element of the standard basis. So pictorially, it looks like this. The 0 is here maybe, and the lattice points are here. Okay. The minimizers in this case, they're just 2 vectors. These 2 elements are the minimizers of L. Let's compute the corresponding functionals. So so the symmetric matrices in 2 dimensions just look like this. It's a 3-dimensional space. The minimizers we said are E1 and minus E1. If you look at this functional, where did it go? If you look at this functional here and you multiply a vector by -1, you don't change the functional. So actually we only have one functional in this case. And what is that functional? Phi E1 of A is this is the formula. So we get this. So it's mapping A, B, C to A. Okay, so we only have one functional, so obviously this is not going to span the dual. So it's not perfect. We can do a similar computation with L being the Z2 lattice, and then the minimizers are plus minus E1, plus minus E2, and the functionals we already computed. We already computed the functional that's associated with E1 over here. The functional that's associated with E2 over here, we can now compute, and it's going to give us C. So I'll just write it down. So 0, 1, sorry. When you do the computation, you're going to get C. So again, it's not perfect. We have two functionals. and they can't span a three-dimensional space. Okay, is this clear? We just don't have enough of them. The case which is part of the exercises is the hexagonal lattice, and these are the minimizers. So L equals hexagonal lattice. These are the minimizers. So there are 6 minimizers. 3 pairs plus minus 1 pairs of linearly independent vectors. And then part of the exercise, which is already on your exercise sheet, is that L is perfect. So you can compute the linear functionals associated with these 3 maximizers, and you see that they are linearly independent in the space of linear functionals. So that's just sort of giving you a taste of what perfect means. So let's write down a proposition that is useful, even though it's very simple. So proposition, if you have a perfect collection, then it has to span Rn. So this is not if and only if, as we already saw in these examples. In the example B here, the 2 minimizers up to plus minus, the 2 minimizers of Z2, they do span R2, but the corresponding functionals don't span the dual of the symmetric matrices. So this proposition is not if and only if, as example B shows, but at least there's one direction here. So here's the proof. Suppose it didn't span, suppose the collection F didn't span Rn. So let's denote that span by V. So suppose V was a proper subspace of Rn. If it's a proper subspace of Rn, you can find a matrix A, which is not 0, and such that V is contained in the kernel of A. You can find such a linear transformation, which is non-zero, where V vanishes on A, and you can also make asymmetric. I'll let you think about why that's true. Okay. If you think about what A might be doing on V, it's sending V is in the kernel of A, and on the orthogonal, you can define it on the orthogonal complement of V in such a way to make it symmetric. So that's an exercise for you. And once you have this matrix, you can then, for all x in F, phi x of A is AXX, 0x, 0. And this is because x is in F, so A times x is 0. So this linear functional gives 0 on A for every x in F, and A is non-zero, so we get a contradiction to the fact that this collection spans the dual. Okay, so this just shows you that a perfect collection has to have lots of vectors in it, at least enough to generate Rn, but obviously more. Here's another proposition. If L is extreme, then the size of the minimizers, the collection of minimizers, is there are at least n times n plus 1 vectors in the collection of minimizers for the lattice L, and the proof, let min L be plus or minus V1 plus or minus Vt for some t. So the number of elements the number of elements in the minimizer is always an even number because every vector comes with its minus, and the span.
So here L is perfect.
I'm sorry, L is perfect. Thank you. Yeah, thanks. Now, as I said before, if you take a vector and compute this linear functional on the space of symmetric matrices, you get the same thing if you multiply by -1. So phi of V1 is the same, phi of Vi is the same as phi of minus Vi for all I. And so the span of this set is the same as the span phi Vi, I going from 1 to t, and it has dimension n times n plus 1 over 2. So this implies that t is at least n times n plus 1 over 2. And this implies that the number of elements in the minimizer is at least n times n plus 1. So going back to our previous example, what we're seeing is that in dimension 2, this number is, in dimension 2, this number here is 6. So what this is showing is that a perfect lattice in dimension 2 has to have 6 shortest vectors. And it's easy to see from this that the only perfect lattice in R2 is going to be the hexagonal lattice. There are no other lattices for which the number of shortest vectors is 6, up to rotating and dilating. So, so this is like a hint for your exercise. So from this, easy to show, and this easy to show is your is one of your exercises, that the hexagonal lattice is the unique up to dilation and rotation perfect lattice in two-dimensional space. Okay, so let me just repeat the theorem that we want to prove next. This is the theorem of Korkin-Zolotarev. Now that we have the notion of perfect, and then we take a break. So if L is critical, then L is perfect. So let's take a 10-minute break, and after the break, I'll prove this theorem.
Baba? 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 Barak, we can't hear you.
Okay, sorry. Thank you for telling me that I was speaking to myself. So let's continue. So I'm trying to give the idea of the proof of this statement of Korkin-Zolotarev. So we're proving the counter positive, namely we're proving that if L is not perfect, then it's not critical. Not critical means that we can locally improve the density of the circle packing by finding lattices very close to L where the density is larger. So let's give the idea, and let's just explain the idea in the particular case of the Z2 lattice that we already saw is not perfect. So idea picture for Z2 lattice. Here's the Z2 lattice. Here are the non-zero points. This is the minimizers of the Z2 lattice, and the lambda 1 is achieved by this particular Euclidean ball, which is trapped between these 4 points of the minimizer. And there, let's draw two other lattice points here. If you think about these two lattice points, you can think about an ellipsoid that's close to the unit ball, but sticks out in the direction of these, in the direction of these other vectors. And this ellipsoid has, we're going to show this is an ellipsoid of area larger than the ball and arbitrarily close to this ball. We can find such an ellipsoid. So then what you're going to do is you're going to apply a linear transformation G that maps E to a ball of radius R, where R is bigger than 1. E is my notation for this ellipsoid. Then what we're going to have then is that GZN is close to L because E is close to the ball, and the lambda 1 of GZN is larger than 1. The reason that the radius of this ball is bigger than 1 is because the ellipsoid has area larger than 1, and where G, a linear transformation G of determinant 1, I should have said. We're going to find such a linear transformation. So linear transformations act transitively. The connection to symmetric matrices is through this picture. Linear transformations act on ellipsoids transitively, and the ellipsoids are given by quadratic forms. And so the ellipsoid G applied to the ball of radius 1. What is this? G is an element now of G. I'm trying to explain just the intuition of why we see symmetric matrices and positive definite symmetric matrices appearing in our discussion. So the ellipsoid you obtain by mapping the ball of radius 1 by G, this is G applied to X and Rn, such that the norm of X is less than 1, which is the same as saying that the inner product of X with itself is less than 1. So this is, just call it U or Y maybe. And this is the same as Y and Rn, such that AYY is less than 1, where A is G inverse transpose G inverse, right? So this is the connection between this proof strategy, which involves deforming a Euclidean ball into an ellipsoid of larger volume, and symmetric matrices is through this link, okay? And that's basically going to be the proof. If the perfectness assumption is violated, we're going to be able to find a symmetric matrices that enables us to find a nearby ellipsoid of larger volume.
Sorry.
To make, yeah.
Above, I got lost somewhere further above. You said GZ to the n is close to L. What is L here?
Where? Oh, this should have been GZ squared. We're working in 2
So
dimensions.
this GZ squared is close to Z square here? That's what you're saying? Or
Yes. Yes.
yes, okay. The L is Z squared.
L is Z squared here. Yes.
Yeah, okay. Fine, thanks.
All right. So that's the basic idea. And to make this idea work, we sort of need 2 pieces of this puzzle. One is we want to understand what happens to the minimal vectors when you apply a linear transformation. And we also want to understand what happens to the co-volume when you apply the transformation, because the quantity that we're trying to understand is lambda 1 divided by the co-volume to the power 1 over n. So let me just formalize some properties that we need in this strategy. So let's define a map from GLNR to symmetric matrices. It's mapping a matrix G into a matrix A of G, and A of G is defined by G transpose G minus the identity. So the way to think about this again is first we take G and we make this positive definite symmetric matrix out of it, and then subtracting the identity moves the picture to it's no longer positive definite, and now might not be positive definite anymore, and this matrix is close to 0. So this is a way of taking matrices in G which are close to 0, close to the identity, and manufacturing symmetric matrices which are close to 0. And the point is that this fills up an open neighborhood of 0 in the space of symmetric matrices. So let me write that down. So there is a neighborhood, let's call it U, of the identity in GLNR, such that V, the image of this neighborhood, is a neighborhood of 0 in symmetric matrices, and the restriction of this mapping, I'm not giving the mapping a name, but if we restrict it to this neighborhood U, is a diffeomorphism from U to V. Diffeomorphism means it's 1-to-1 and onto with a differentiable. It's a differentiable map, and the inverse is also differentiable. And the proof, you've all seen this kind of statement before, even though maybe not in this terminology. This is just the open mapping theorem from Calculus 3. Well, maybe not all of you, but I hope if you haven't, you should check out what the open mapping theorem says. When you have a mapping from an Euclidean space of some dimension to another Euclidean space of lower dimension, and the mapping is if the derivative mapping is surjective, then at a point, then there's a neighborhood of the point where this differentiable mapping becomes a diffeomorphism onto its image, and that's exactly what this. You have to make a computation that says that the conditions of this open mapping theorem are satisfied. So let me write that as an exercise. It's not on your exercise sheet. We're not going to we're not going to prove it. If you don't remember what the open mapping theorem says, or you don't want to work with it, just go back to this. Basically, I gave you the map and the inverse. Where was this discussion? When we discussed this here, this is a way to recover this. Basically, this is a way to recover G from A. Okay, if you have A, you add identity to it. If A is small, it becomes a positive definite matrix, and then the mapping B plays the role of G. So this is basically the inverse. So maybe we can call this computation, give it a color, call it this star, and star is basically the inverse map. Okay. So we're going to need this fact. Let's also note, and maybe add that to this proposition. I'll make the proposition a little bit longer. Let's also note that the set of things that go to 0 under this map is, so G is in U, A of G equals 0. This happens if and only if G is orthogonal. Yeah. Okay. So we're going to need this. This is the orthonormal matrices. Orthogonal matrices in R. So this is an easy check, and we're going to need this proposition. Now some lemmas for the proof. Lemma 1. For any lattice L, there's a neighborhood U of identity in GLNR such that for all G and U, the minimizers of the new lattice that you get GL by mapping G, applying G to L, are a subset, maybe all, but maybe fewer, of the minimizers of L pushed by G. So another way to say this is, if your G is close to the identity, the shortest vectors in G are coming from the shortest vectors of L, not from any other vector. And this is just continuity, basically. So yeah.
Can I ask something about the previous claim just now?
Yeah.
That is it so? How exactly is Gita A of G a diffeomorphism if it's not?
Oh, I'm sorry. Right. It's not a diffeomorphism. It's an open mapping. It's you're right. The dimensions are not the same because it has a kernel. Yeah. So it's an open mapping. Thank you.
Okay, thanks.
Open, surjective, and smooth. Right. And this, thank you. And this is not the inverse, it's an inverse. So this is just showing, thank you. This is just showing that it's surjective on a small neighborhood. This argument with this strange color, with this yellow color, is just showing that there's a neighborhood that you get mapped onto. Thank you. So proof. So L is given, it has its collection of minimizers, and all the vectors that are not minimizers are longer by some amount. L is discrete. So since L is discrete, there is some positive number, which I'll denote by eta, such that if V is some vector in L, V is not 0, and V is not a minimizer, then the length of V is, let's make it strictly bigger than 1 plus eta times lambda 1 of L. So all vectors which are not the shortest are longer by some definite amount by discreteness. So now let's define this neighborhood U such that its distance in the operator norm from the identity is less than half eta. So then for all minimizers, if V is a minimizer of L and G is an element of U, then the length of V is lambda 1, and the length of GV is, by the triangle inequality, less than, it's strictly less than, yeah. Right? This inequality is just the triangle inequality because this says GV minus V. This length is equal to lambda 1 of L. That's what's written over here. This length is less than eta over 2 times lambda 1 of L because of the restriction on the operator norm. And so the sum is smaller than 1 plus eta over 2. So you're seeing that if you take a vector which was a minimizer, then its length can only be at most this number. On the other hand, if V is in L and it's not a minimizer and it's not 0, and G is in this open set U, then the length of GV, again by the triangle inequality in the other direction, is bounded from below by this number, I'm sorry. Yeah. Sorry. So this is bound. It's I may have made a small mistake here with the constant. So let me just write it down and make a little, I don't want to spend too much time on this. I think there might be a little issue here with this constant. So let me just, this will be corrected in the notes. So this is a little bit off. I'm just noticing. I'll correct that in the notes to the lecture. But in any case, I can choose this eta. What am I just proving? I'm choosing this quantity small enough so that vectors which are normalizers only grow by a small amount, and vectors which are not normalizers, they're too long. This length is bigger than 1 plus eta, and they become smaller by their operator norm times their length, and they can't become smaller than this amount. I think I made a small mistake here. I was thinking that this is lambda 1, but it's not lambda 1. So I'll fix that later in the notes, but the idea I think should be clear. Okay, I'm sorry I'm rushing a little bit. I just want to give you the proof of the theorem. We're almost there, so this will be fixed in the notes. And so as a consequence of this, let's call this lemma 2. For any L, we get a neighborhood. Let's call that curly V of 0 in the space of symmetric matrices, such that whenever you take symmetric matrix in V, which is of the form A of G for the mapping A that we had before, then the shortest length of the shortest vector squared for G times L is the length of the shortest vector squared for L plus the minimum over the minimizers of L of the quantity phi V applied to A. The phi V is this linear functional on symmetric matrices that we had before. And so now you're seeing where this linear functional comes from. It's what happens, an upper bound on what happens to the length of the shortest vector. So the proof is, this is just, another thing you're seeing somehow is that when you work with these linear functionals, it's natural to square these numbers. We have this Hermite constant where the lambda 1 was squared, and this little lemma sort of explains where the square is coming from. So let's prove this. This is just a one-line proof from the previous line. By lemma 1, in order to compute lambda 1 of GL, where G belongs to that neighborhood that appears in lemma 1, suffices to consider vectors GV, where V is a minimizer for L. And for such a vector V, it's the length squared is so this is V G transpose GV, which is V identity plus A V, which is the norm of V squared plus the norm of, which is, which is V AV, which is the norm of V squared plus phi VA. Okay? And so all the vectors in the minimizer, this quantity is lambda 1 of L, and we're squaring it. And the amount that we have to add is this linear functional phi V. And that proves lemma 2. Now, remember that the quantity that we're trying to maximize is, we are trying to maximize the quantity lambda 1 of L divided by the co-volume of L to the power 1 over n. And Manuel asked previously, why is it that we insist on working with general lattices and not lattices of co-volume 1? If the lattices were of co-volume 1, then the term that you see over here would not bother us. But somehow this analysis is easier if we allow G to be arbitrary. When we allow G to be arbitrary in GLN, not necessarily of determinant 1, then this fact about, where did this go? This fact in the proposition about this mapping is clearer. If we restricted G to be of determinant 1, then we'd have to understand precisely what the image would be here, and this would be a little bit complicated. So we pay the price. We understand the mapping better if we work with GLN. The price we have to pay is that we have to worry about this co-volume. denominator. So now the co-volume is affected when you replace L by G of L. The co-volume is affected by the determinant of G. So now I want to analyze how the determinant of G behaves near the identity. So to understand denominator, you need to understand the determinant of G for G close to the identity. So that's just an intuition. Here's the precise statement, which I'll call lemma 3. There is a neighborhood. In all of these statements, you're seeing neighborhoods always being denoted by curly V, but of course they may each be smaller than the other, so we can always assume one neighborhood that appears is contained in previous neighborhoods. I don't want to compute the notation by giving them different names. So there's a neighborhood curly V of 0 in the space of symmetric matrices, such that for any A, which is A of G, in this neighborhood, as long as its trace is non-positive, either J is orthonormal or the determinant of G is less than 1. So another way to say this is that determinant of G greater than or equal to 1 gives a strictly positive trace. Or if the trace is smaller than 0, then the determinant has to be strictly smaller than 1 unless we do nothing. So let's first just do a reality check and make sure that this lemma makes sense, because this is related to a previous question. This says A equals A of G, and as we saw, the mapping A maps to A of G is not one-to-one. But how, in what sense is it not one-to-one? If you change, if you have two different G's that map to the same A, then they differ by an orthogonal transformation. If they differ by an orthogonal transformation, then their determinant is the same. So I'll add that as a remark very quickly. Remark, if A of G1 equals A of G2, then G1 equals GTO, where O is an orthogonal transformation, and therefore their determinants are the same. So that's,
But
otherwise this would
there are orthogonal elements with negative determinant.
I'm sorry, the absolute value. Yeah, but we're close to the, we're in a neighborhood. Yeah, we're in a close, we're in a neighborhood of the identity, so we can't have negative. We're in a small neighborhood of the identity.
The factor is on the left, no? The O. You
Uh,
map to G transpose times G.
So A maps to G transpose.
Or am I?
Yes, you're right. Yeah. Right. Okay, so this O goes away when you map to G transpose G. Well, I see that I'm slightly over time, so let me postpone the proof. Maybe I'll have time to complete it now. And so let's postpone the proof. Maybe I'll have time to complete it today, and maybe I'll do it next week. This is a calculation that's going to be important for us next week as well. Let's use this to complete the proof of the theorem, and then come back to this if we have time for the proof. So proof of the Corkins-Zolotarev theorem assuming this lemma. Let me remind you what the Corkin-Zolotari theorem said. It said that if you're critical, then you're perfect. Where did this go? Here we go. If your lattice is critical, then the lattice is perfect. And what's the definition of perfect? You take the minimizers of L, so the shortest vectors in L. For each one of them, you have this linear functional, and these linear functionals should span the space of linear functionals on symmetric matrices. So let's prove it. So suppose suppose L is critical, and suppose by contradiction that in any neighborhood, I'm sorry, suppose by contradiction that the lattice is not perfect, which means that there exists a symmetric matrix A, which is not zero, such that for all the minimizers, Px A is zero. Okay, so this is what you get by assuming that the lattice is not perfect. If the lattice is not perfect, then these linear functionals don't span all the linear functionals on the space of symmetric matrices. And so there's a symmetric matrix which is not zero and for which this is satisfied. So by replacing, if necessary, A with the minus of A, we can assume that the trace of A is not positive. And by replacing A with S times A for some positive small parameter S, can find such A arbitrarily close to zero. For each small s, let GS be an element of GL and R such that A of GS is S times A. So since, let's go back to lemma 3. So I'll just write something down. So since SA is not zero, G of S is not orthogonal. If GS were orthogonal, then A of GS would be zero, but we already know that, where is this? We already know that A is not zero. So S of it, this is not zero, and if G of S were orthogonal, then G of S, then A of GS would be zero. So we know that GS is not orthogonal. Then we go back to lemma 3, and this is not true. So the determinant of GS is strictly smaller than 1. By lemma 3, the determinant of GS is strictly smaller than 1. And by lemma 2, we can, by lemma 2, lambda 1 of GL equals lambda 1 of L. Let's look at lemma 2. we chose A so that these numbers are 0. So for every one of these vectors, these numbers are 0, and so this equals this. So taking square roots, lambda 1 of GL equals lambda 1 of L. And so we get that, and therefore the quantity lambda 1 of GL divided by the covolume of G, so this is GS. The numerator is the same for all S. It's lambda 1 of L. This would be an S, sorry. And here we took the covolume of L to the power 1 over n, and we multiplied it by the determinant of GS to the power 1 over n. But this quantity is less than 1. We're taking 1 over that, so this is bigger than lambda 1 of L divided by the covolume of L to the 1 over n. And so L is not critical.
So also in lemma 3, the statement, I was a bit confused. The statement there is that the absolute value of the determinant
We're in
is...
small neighborhoods. Did I say small neighborhoods?
I
Yeah,
guess-
okay. The notation, just the notation, G is only defined in a small neighborhood of
the identity.
the mapping G maps to AG is only defined in a small neighborhood of the identity, and we can take that neighborhood so that the determinants are all positive in that neighborhood. Okay, so we're just out of time. So lemma 3 is something that I'll prove next week, and I'll prove it with more detail because we're going to need an improvement of it for proving the other statements. Okay, great. So see everybody in a week. See you next week. Stop recording.
Thank you.